All right, thanks for coming. So in the next 20 minutes or so, I'm going to share with you some of the major developments in Spark that happened in the past few months and also going forward. I figure we'll actually go nerdy a little bit, going back to our engineering roots, and talk about even some of the internals that might be quite different from the other keynotes we have here. So for a lot of you have already seen this stack diagram of Spark. At the core of it, you have the Spark core engine that sort of exposes the RDD API. And on top of it, people over time, the community have built a variety of domain-specific libraries, including SQL, streaming, MLlib, and GraphX for graph processing. However, when I think about the development, I actually have a slightly different view of the stack diagram. I think with this stack might be a better way to actually represent a lot of the development that's happening. And what do I mean by it? In this stack, we'll actually slice a line in the middle to cut Spark in half into the front end and the back end. So the front end consists of user-facing APIs that actually normal application programmers interact with daily. And the back end is what's responsible for the distributed execution of the Spark programs. So some of the concrete examples of the front end and the back ends are the RDD API, the data frame API, the machine learning pipelines, and the APIs in GraphX would go into the front end. And the back end includes a scheduler, which is responsible for how you dispatch different tasks in the distributed engine, the shuffle operation for data exchanges, and all the variety of physical operators in Spark SQL. All of those go into the back end. So the last 12 months actually witnessed some of the most active developments in Spark, the history of Spark since the project started. And there's a lot of major changes to both the front end and the back end. In particular, to the front end, there's data frames, there's the new data source API that actually makes Spark play nicely and integrate extremely well with a variety of different data sources in the existing ecosystem. And there's also the R new language front end, for the new data scientists already familiar with R, and machine learning pipelines. In the back end, we started the project Tungsten about 6 months ago, and there's also a lot of other changes that happened. So in the remainder of the talk, I'm going to zoom into two of the changes, data frames and Project Tungsten, and try to connect them, even though the two are similarly orthogonal concepts. So first, data frames. Spark data frames, as most of you probably already know if you're sitting in this conference, it's essentially a data frame abstraction, a scalable data frame abstraction for both single node and distributed setting. It exposes the API that's very similar to the data frame API in a variety of different programming languages and a single node. So for examples include the Python pandas and R's dplyr. As a result, it's actually much easier for new data scientists and programmers to learn this new API. In the past, when we talk about the RDD API, you sort of have to understand what functional programming is before you can use Spark. But with this new data frame API, it becomes much easier to use and get started. However, data frames actually goes a lot deeper. The significance of data frames actually goes a lot deeper than just the front-end API exposed to the users. And in order to explain that, I have to first explain sort of how the RDD API is being executed, programs written in the RDD API is being executed in Spark. In the RDD API, the API essentially expects user-defined functions, or sometimes you might call them lambda functions or closures in the respective programming languages. So for example, you have a Java API or Scala API would take in the closures. And then the closures are operating on sort of opaque Java objects that Spark doesn't really understand, as Matei hinted at in yesterday's keynote. So in order to actually execute these functions, and in order to actually pass objects to these functions, we have to run everything in the JVM, rely on exactly the same type of objects we have. Same thing goes for Python. If you write a PySpark program, what you will pass to Spark is the lambda functions in Python, and those expects Python object as inputs and Python object as outputs to those functions. As a result, the only way we can execute them is to run them in the Python process. Now, let's go to the data frame API. The data frame API is actually fairly different. The way it works is when you're programming the data frame API, you are essentially specifying the way, the logical semantics of your computation in a domain-specific language. So when you do 1 + 1, it's not really passing the JVM bytecode or a lambda function to Spark. It's actually constructing an expression that indicates 1 + 1. And all this gets transformed into an intermediate layer called a logical plan. And then, if you've gone to Michael's talk yesterday about the Spark SQL, the logical plan goes through a relational optimizer called Catalyst to be optimized, and then a Catalyst generates actually the plan for the final execution. So this is actually the back end of the back end, which is the physical execution plan. So if you look into actually the data frame implementations for different variety of languages, they actually look fairly simple. And the reason is they're really just wrappers around the logical plan, this intermediate representation. As a result, one of the benefits of the data frame API to Spark, not necessarily to the end users, is it's actually much simpler to build new language front ends using the data frame API. For example, the Python data frame front end was actually built over the course of a weekend by one of our engineers in about 2,000 lines of code. Of course, it's expanded over time, but that sort of explains how simple it is to build this whole new language API. And similarly, the R API took about only 1,000 lines of code. And as I know now, there's actually a lot of new language front ends that's being built by the community, including Haskell and Clojure and all of those. The second benefit, which some of you already seen in the slide, is performance. When you use the RDD API, when you use Python, because the Python RDD API has to be executed using a Python process across a cluster, Python natively runs slower than the Scala or Java. However, in the data frame API, because all the front ends are really just wrappers, converting them to the same logical plan, and then the same logical plan gets turned into a different physical plan for execution. So they really are all running the same code under the hood. As a result, you actually get the same performance for all the different languages we have in Spark: R, Python, Scala, Java, and even SQL. Now, next, Project Tungsten. In order to explain Project Tungsten, I have to sort of walk through history of the last 5 years a little bit. When Spark first started, it was, I think, in late 2009, early 2010. And we're going to take a look at the hardware resources that were available back in 2010 along 3 different dimensions: storage, network, and CPU. So in 2010, most of the world were running on spinning disks. And each of the spinning disks can probably pump out about 50 to 100 megabytes of throughput per second. And the predominantly data center networks are running at 1 gigabits. And CPU was around 3 gigahertz. Now, fast forward 5 years, 2015. What are you buying in your own data centers? Or what are you using in the cloud? In 2015, SSDs are becoming very common. As a matter of fact, in order to find a non-SSD instance on Amazon EC2, you actually have to look pretty hard to find one. Each of the SSD can pump out about 500 megabytes of throughput. And 10 gigabit networks are very common. And as a matter of fact, 40 gig networks are also becoming increasingly popular. CPUs, actually, on the other hand, hasn't really changed that much. The frequency of CPUs really hasn't changed, even though the density and the number of cores have increased a little bit. Now, when we first started Spark, because network and storage were the primary bottlenecks, we spent a tremendous amount of effort optimizing network and storage in the past 5 years. And as a result, when we actually profile most of the Spark applications, we realize they're all CPU bound. If you take a look at your hardware monitor, resource monitor, you realize you're not saturating usually your disk or SSD throughput, and you're not really saturating your network bandwidth, and your CPU is spinning at almost 100% full. Sometimes even things as simple as just reading data, scanning data to decompress your compressed data could saturate the CPU. So Project Tungsten is started about 6 months ago, aimed at substantially improving the CPU efficiency of Spark applications through 3 different methods. One is dynamic code generation, or we call it runtime code generation. This is our Spark to actually generate very efficient code, bytecode for execution, to eliminate all of the possible virtual function overheads and boxing of the data structures in the JVM. And the second is to rewrite a lot of internal algorithms to employ variants of them that's much more cache efficient. And so as a result, most of the time, Sparks are reading from the L2 and L3 cache of the CPUs rather than reading from memory. And last but not least is off-heat memory management. If you had profile Spark application before, often you realize a lot of the performance actually goes out of the window because of the JVM garbage collection. By actually actively managing our memory ourselves in Spark, Spark actually knows more information about the application and can manage it better than JVM does. Now, the interesting thing about the Tungsten project is all the three actually requires knowing more about the semantics of the application, including sort of the layout and the structure of the objects you have in the program. That was actually pretty hard to do in the RDD API. Now, the interesting thing is, with the data frame API, Spark actually knows almost about everything that it needs to know in order to optimize this program further. And as a result, the Tungsten project is really only enabled by a lot of the work in the data frame API, including logical plan idea and the relational optimizer. Most of the Project Tungsten work, or most of the initial phase of Project Tungsten work, has been merged and is already available in Spark 1.5, which will release in September. There's actually going to be a lot more work coming in 2016. Now, let's look forward a little bit to 2016 and see what are some of the more exciting things that's coming. I picked three things that's actually really exciting about me personally. And you actually, as soon as I explain them, you realize they're actually a continuation of the two of the things I just pointed out, data frames and Tungsten. So the first is the Dataset API that Matei kind of alluded to yesterday. When we first released data frames, a lot of people were really happy. A lot of new data scientists told us, oh, I don't have to spend hours learning about functional programming anymore. I can now just get started with Spark. However, we also started getting a lot of requests over time. And one of the most popular requests was, data frame is great, but I have my existing libraries that have specific objects or class types that I expect, and I want to use those libraries. How can I use them? And the number two request was, I want my type safety in Scala and Java. Data frame was great. You have the API that's already native in R and Python. There's not really types there. But when I'm writing a very large application across many different teams, I want stronger type safety. Give me that. And that's also actually Martin hinted at. So Dataset API is actually a new experimental API we're introducing in Spark 1.6, which will be released in about a month. It essentially provides a typed interface over data frames, and as a result, also over Project Tungsten internals. What it does is it allows you to define essentially arbitrary Java objects or Scala objects as you want. In this case, have a Scala case class called person. And then you could read in a data frame, and then you can convert any data frame directly into this new abstraction called dataset that's typed, just by calling .s and passing it the class type. And once you have a Dataset API, you could actually apply a lot of the functions that's available on the RDD API directly to the Dataset API. For example, filters, you could run reduce, you can run group bys. And also, you can easily convert it back into the data frame API just by running aggregations or using existing functions that's available in data frames. Now, some of you might start wondering, what really is this thing? I just spent a bunch of time explaining why it's hard to optimize arbitrary objects and arbitrary opaque JVM functions. So what's the benefit of this thing? And the reason is the magic really lies in this concept called encoder. In the Dataset API, there's actually an implicit encoder that you need to specify. And most of the time, if you're using Scala, it's infer automatically for you. And this encoder essentially tells Spark what this data type is and how we can map it into the Tungsten types. So we can actually pack all these data types or the specific objects in memory in a very optimized way and leveraging the existing Tungsten backend. I don't have time to go into a lot of details for this, but we actually grabbed a really exciting Jira number, Spark 9999. So if you search for Spark 9999, you can find a lot of details about this new Dataset API and how the encoders work. And the first experimental version will be released in about a month. And this probably will become Dataset plus data frames will become, I would say, the main abstraction going forward. The second thing I'm really excited about is streaming data frames. If you pay close enough attention, you realize Spark, we have the data frame support. Spark SQL is already natively runs data frames. Machine learning pipeline is running on top of data frames. Spark streaming, however, really doesn't have a lot to do with data frames yet. And Spark streaming, or streaming data frames, just as the name indicates, is really to push the data frame concept also to Spark streaming. In order to provide a much easier to use API that combines, I think, batch streaming and interactive data analysis over streaming data. And one of the nice things about the data frame API is we have this unified data source API that we can actually read data in from a variety of different sources, even though they look, in terms of programming code, they look almost identical. This will also apply and carry over to the streaming data frames work. We have a unified data source and data sinks API for streaming data frames, and we also, because of the use of data frames, the Spark streaming, we'll be able to actually leverage a lot of the work that's going on with Project Tungsten. And last but not least, we have gotten a lot of requests about out-of-order data support. This is data that arrived much later than when they were generated. We will be adding native support to that for Spark streaming data frames. And I want to end this talk with just the very last item. And before that, I have to sort of just show some hardware trends again. In the beginning of 2015, Microsoft announced having a VM support for up to 448 gigabytes of RAM on a single machine. And just a couple of weeks ago, Amazon Web Services announced support for a new VM type that will be available next year, up to 2 terabytes of RAM on the single node. So 2 terabytes of RAM in a single node. This effectively means a lot of the data for big data problems can actually fit onto a single machine. Another thing that's fairly interesting is in the middle of the summer, Intel and Micron announced this new technology called 3D Crosspoint. And 3D Crosspoint has 3 different kind of attributes. One is its latency is almost as slow as DRAM. And its capacity, or just the cost of it, is almost as cheap as solid-state drives. And last but not least, it's byte addressable, which means you could actually address any bytes in the 3D Crosspoint storage, making it much more similar to memory than solid-state storage. As a result, you could really view it as a new extension for memory that's so now you have access to almost the size of SSDs, but in a memory fashion and latency. And all of this is really just showing you that hardwares are becoming more and more powerful, and a single node machine can become a lot more powerful. As also shown just in the Dell booth outside. Now, unfortunately, a lot of software needs to change in order to actually leverage some of these newer technologies and to leverage some of the power of the new single node systems. It doesn't actually just work by running Spark or running a Python program or running an R program on a larger machine. You realize at some point getting diminishing returns because the software can't really keep up with the hardware. That's one thing that's really exciting about the data framework and the Project Tungsten work, which is now, because we can capture the semantics of the computation in the different language front ends, that all gets consolidated into this logical plan, we could actually generate, using code generation in Project Tungsten, different backends for different runtimes that's optimized for those runtimes. So today, in 2015, Spark runs in the JVM, and runs well, probably up to hundreds of gigabytes of RAM on each of the node. But tomorrow, it's very possible Spark can actually run a variety of different technology backends, including LLVM, leveraging the vectorized instructions in the modern CPUs, or leveraging the 3D crosspoints, just based on this concept of logical plan and code generation. So just to end my talk, there's only one takeaway. If some of the stuff were too geeky for you, just remember that data frames and its sibling datasets API will become sort of the new abstraction that permeates a lot of the stacks in Spark. And all the components up there, SQL, Python, R, streaming, graph, machine learning, will all be running on top of data frames and datasets. And they will all get executed in this new Tungsten backend that can selectively be optimized for a lot of different runtimes. Thanks. I think that's the end of my talk.